All right, so let's go ahead now. In the previous video, we were working on the chapter 10 problems. Now I'm going to work on the chapter 11 problems. And I just picked some selected problems off of the chapter 11 quiz. All right, so in this one, it says, here we're going to be drawing a single card from a standard 52 card deck. And we want the probability and then also the odds in favor that you do not draw an 8. Okay. All right, so one way to think about it is that out of those 52 cards, there are 4 8s, which would simplify to be 1 out of 13 is the probability that you do draw an 8. And so the probability that you do not draw an 8 would be 1 minus that, which would equal 12 out of 13. Or if 4 of them are 8s, then that means the remaining 48 would not be 8s. And 48 out of 52, when you simplify that, would simplify to be 12 out of 13. So those are the two ways to get that answer. Okay. All right. And then the difference between probability and odds we're working on. For probability, the number that are in favor of the event happening, so there are 12 out of 13 total that you do not draw an 8. What you do for odds is you say odds in favor of not drawing an 8 would be 12 to 1. Okay. So probability is 12 out of 13, and odds would be 12 to 1 in favor that you would get something that's not an 8. Tricky part on that one, I think, is that they have the word not in there. So it makes it kind of like a double negative. Okay. All right. Now this one, what number are we up to then? I can't remember what number we were on. So I'm just going to start them over, the chapter 11 problems. Let's just call that the first one from the chapter 11 set. Okay. In this question, we're going to roll a single die and find the probability of rolling an even number or a number less than 3. So we can list the sample space and we can just count. So here's the even numbers. And then we also could be a number less than 3, which would be either 2 or 1. So all total, that would be 4 out of the 6, which would simplify to be 2/3. That's where they get the 2/3. So if you actually have the list of the sample space, you can actually count them to find it. All right. If you use the formula, you could think about doing the probability of getting an even number, which would be 3 out of 6. The probability of a number less than 3 would be 2 out of 6, 1 or 2. But you can't double count, so you have to take away the probability of being even and a number less than 3. So you take away the 2. You don't want to double count it, and that would also get you to 4 out of 6. Okay. All right. Now, the next problem, so this would be the third one from the chapter 11 set, is finding the expected number of girls in a 4-child family. So we could go through and make a list of the all the possibilities by doing the tree. Could be girl or boy. Okay, and then each of those could be a girl or boy, and we could keep going like that, right? Let me just do a few so you can see it. So you'd have all these branches once you finish it. So you had 2 possibilities for the first child, times 2 for the second, times 2 for the third, times 2 for the fourth. And that gets you to 16 possibilities. That's why you see the denominator of 16 there. All right, now to be able to figure out where they got these probabilities, you'd almost have to have this list. So it could be all girls, it could be girl, 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 boy, right? And then what we can do is kind of imagine, do a systematic listing or do our tree and list them. So it could be girl, girl, boy, girl, 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 boy, boy. Or we could go to the girl, boy, girl, 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 boy, girl, boy, girl, boy, boy, girl, and keep going until you get everything done. So now I'm done with all my girls. Now I'm going to start with boy and do the same thing. But you see these 8 right here, and then I'd start with boy, girl, 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 boy, girl, girl, boy. And I could keep going. But here's something that we've been observing. So if I'm wanting my variable, my x, to be the number of girls in the family, wouldn't we have one possibility down at the bottom, which would be all 4 boys? And that would be out of the 16 possibilities. So that's where that 1 out of 16 comes from. Okay. And then if we went through and we counted getting girls, just having 1 girl, we would look for the options where there's just 1 girl. Okay. We have 1 there, we'd count those up and see what that probability would be. So there'd be more of them in this area down here. You just don't see it, but that's where the 1/4 came from. It was that there were 4 possibilities out of 16. And then for 2 girls, you'd look for everything that had exactly 2 G's in it. And so you'd count those up, and that would have turned out to be 6 out of 16 if I had completed my list. And then there's symmetry going on. For 3 girls, we'd be back to 4 out of 16. And then for 4 girls, okay, there's only 1 possibility with all 4 girls. There it is, out of the 16. Okay. All right. So now we're being asked to complete the probability distribution and to come up with the expected number of girls in the 4-child family. So what we're going to do is multiply this times that. So 0 times 1 over 16 would be 0. Okay. Then 1 times 1/4 would be a 4th. Okay, 2 girls, probability of getting 2 girls. Simplify that, we'd get 3/4. 3 girls times the probability. By the way, 4/16 reduces to a 4th, so you'd actually put 1/4 in when you typed it in. And then when you multiply 3 times 1/4, you get 3/4. And then the probability getting all 4 girls would be 1/4. No, it wouldn't, 1/16. When you multiply by 4, that would turn out to be a 4th. Okay. And so then what you do to get the expected value is you add all of those, don't you? So that's 1 and 1 gives you 2. So the expected value would be 2. Now the question is it reasonable that if you had 4 children, would it be reasonable to expect 2 girls? Okay. So that's what this second part's getting at. And boys and girls are basically equally likely, so you'd expect half of them to be girls. So I like the way the first sentence sounds on these first 2, like this one's out and this one's out, because boys and girls are basically equally likely. And then, so half of 4 would be 2, so the answer for the expected value agrees, so this would be it. Your choice would be B. Okay. All right, let's take a look at this next problem. This one seems kind of long. I'm going to give myself a little more space. All right, so this is the one where we're rolling a pair of die. So I'm going to do a product table and look at all the possible sums. I'm just going to do the sums, not the actual outcome. So the sum could be 2, 3, 4. Let me get all those on there. I'm just adding up what the 2 die would add up to be. There seems to be a nice pattern that allows me to do this kind of fast. Ooh, I got carried away there. Hold on. I was just going to town. This is actually 6, 7, 8, 9, 10, 11. This is the second time I've done the video. My battery died and I had to start over again. So I'm kind of tired of doing it. All right, so there we go. All right, so now what we need to do is we need to get our probability distribution table where X is the sum, possible sums, and then we got the probability of getting that sum. So we have to think about all the possible sums, and they go all the way from 2 to 12, don't they? Right? Once we get started on it, we'll notice a pattern that we can use to complete it. So the probability, that's supposed to be a B, the probability of getting a sum of 2, there was only one outcome that was a sum of 2, and that's out of the 36 possible outcomes. There were 2 that wound up being 3. There were 4. Nope. There were 3 that wound up being 4. There they are. So that turns out to be 1/12. There were 4 that turned out to be 5. There were 1, 2, 3, 4, 5 that turned out to be 6. 6 that turned out to be 7. But there's not 7 that turned out to be 8. See how now we're back down to 5? Then 4 that turned out to be 9. Then 3 that turned out to be 10. And then 2 that turn out to be 11, and then 1 that turns out to be 36. And you would put in the simplified version of each of those fractions. So if it does simplify, you need to do that. If it does reduce, in order to get it correct. Okay. All right, now I'm not done. That's just the probability for each of those. Now, the payoff is that I get $7 times the sum of the numbers that appear on the die. Okay. So one way to think about this is to say, okay, if the sum is 2, then my payoff, I'm going to just do a little column over here, would be 7 times that. So let me just do 7 times each of these so you can think about that payoff amount. You don't have to calculate it. 7 times 7, 7 times 8, 7 times 9, 7 times 10, times 11, and times 12. Okay. So those are the payoff amounts. That's what you multiply by the probability. All right, so what you're going to work out is 14 times 1 over 36. Then you're going to do 21 times 1 over 18, and so on. 28 times 1 over 12. Keep going. Make sure I don't mess up the line. 42 times 5 over 36, plus 49 times a sixth, plus 56 times 5 over 36. Now, if you want to keep the number smaller, and if this makes sense to you, it'll work as well. 63 times 1 over 9. You could do it without the payoff, without the times 7, and just multiply by 7 at the end, and you would get the same answer. But conceptually, I think it's a little harder to understand why. So that's why I didn't show it that way. Okay, then 77. Let's see, what am I up to? 77 would be getting an 11, which would be 1 out of 18. And then 84 would be the payoff if you get a 12. And there's a 1 out of 36 chance that that would happen. Okay, so this right here, you got to type in and work out. Okay, so you can pause this and go ahead and do that. I've got to do it myself. And I'm just typing all of those in. Hopefully I don't make a typo. My calculator allows me to see what I'm typing in, so I can hopefully catch any issues. Let me not talk while I do this. Let's see, it was on 63. Okay, so plus 70 times 1 out of 12. 77 times 1 out of 18 plus 84 times 1 out of 36. And I wound up with 49. Okay, once I did all of that, that equaled 49. Okay, so that would be $49 would be my expected payoff. Okay, and that's the expected payoff. So that would be 49. Is it a fair game? Yes. Because if the expected payoff is 49 and I paid 49, then I got 49, but I paid 49. So my net would be 0. And that's what it takes to be fair. Okay. All right, so that was kind of a time-consuming one. All right, and that was the fourth one. And it wasn't question 4 on the quiz. I just did selected problems off of that quiz. All right, and then this one, question number 5, is another expected value problem, but it just feels different. So here they've already done the chart. So like there's a probability of 0.05 or 5% probability that one person will be absent on a given day. And for instance, there's an 11% chance that 5 people would be absent on a given day. And our job is to find the expected number of absentees on a given day. So what we're going to do is we're going to multiply these together. Okay, 2 times 0.11, 3 times 0.25, and so on. And then once we get those values down here, we're going to add all of those up. Okay, so you don't have to show what you get at the bottom of all of this. You just have to make sure I'm clear what it is you're trying to do. So I'm going to go in and do on my calculators. I know 0 times 0.01 is 0, so you don't really have to type that in. But then 1 times 0.05 plus 2 times 0.11 plus 3 times 0.25 plus 4 times 0.38 plus 5 times 0.11 plus 6 times 0.09. Hit enter, and I get, oh, there it is. I get that right there, 3.63. Told me to round to 2 decimal places, but it actually turned out to be that. So on any given day, I'd expect there to be around 3 to 4 absences. Okay. All right. And it told me to round to 2, so that's why I did that. But like, you can't have a part of a person there. So, if you wanted to say, oh, around 4 absences, I would give you credit for that.